For the past few weeks, we've been operating under the assumption that beams have an internal tension force, and that internal tension force will act on anything that beam is connected to. In particular, especially when looking at the method of sections, if we were to mentally cut a beam, that beam would become two beams, each acting on the other with this internal tension force. For this week, we are going to expand this repertoire of internal forces to include internal shear and internal moment. Figure 7.3 in your text shows what is meant by these internal forces and the sign convention that we often use. So the first type of internal force, which your text has started calling the normal force, but I'm going to keep referring to as tension, is this force right here. You take a section of a beam and you pull outward on it. This tension force acts along the axis of the beam. And by the sign convention that we use, a positive tension force is pulling outward, meaning on the right side of the beam, it's being pulled to the right, and on the left side of the beam, it's being pulled to the left. These two tension forces, and in fact all of these forces, need to be in opposite directions, both for reasons of Newton's second law and Newton's third law. In Newton's second law, if we have a beam in steady state, that is, it's not accelerating, meaning net force on it is zero, these two tensions should be equal in order to add up to zero. For Newton's third law, remember again that if we cut a beam, that both pieces are acting on each other, which means that they will need to act on each other with the same magnitude, but in opposite directions. Another thing about sign convention. In the past, I have been fairly laissez-faire about sign convention. I will have a sign convention that I prefer, but I will accept any sign convention that you prefer, and there are reasons to use other sign conventions. However, when dealing with shear and moment, because of the way they interrelate, I am going to require that you use the sign conventions I'm about to describe, because things can get really wrong if you switch them up. So shear is an internal force, like tension, but where tension goes along the axis of the bar, shear goes perpendicular to that axis. For most of the problems we will be dealing with in this class, we only worry about one direction, but since a bar is a three-dimensional object, there are two directions of shear. There are in a real situation. But again, we are only going to focus on one direction of shear. By our sign convention, we use that a positive shear on the left of the beam applies an upward force, and on the right of the beam provides a downward force, with a net effect that a positive shear will try to create a clockwise rotation in the bar. The third internal force is internal moment. Now, typically we've thought of moment as something related to but kind of separate from the force. And while that is true, this internal moment actually comes from you can think of it as it actually coming from a tension force that is not uniformly distributed. So our normal tension force right here, we can think of it as spread out evenly throughout the entire bar, acts through the center of the bar, etc. But for an internal moment force, we might say that up here at the top, it's a negative tension, and down here at the bottom, it's a positive tension. The net effect, if you integrate all of that tension over the entire cross-section of the bar, is zero force. So we do not include it as a part of tension. But it will have the effect because of basically being a force couple on either end of the beam, and thus creating moment. So a positive moment by our sign convention creates a clockwise rotation when applied to the left of the beam, and a counterclockwise rotation when applied to the right of the beam. For a beam that has a positive moment in it, it will tend to curve such that it's concave facing upward. In order to find the internal forces on the beam, one thing that we can do is mentally break the beam at the point we want to find the forces of. Now, when doing this for the method of sections, we mentally broke those beams to find their tensions on an object as a whole. But we generally assume that there was just the one force acting in just the one direction. For shear and moment, generally these are the results of some loads being placed on the beam. This load could be a point force, something applying a force at a particular point on the beam. It could be a distributed force, something that we saw earlier as the W function. And it could even be the weight of the beam itself, which would tend to act like a W function of constant magnitude. So to find these internal forces, break the beam, and then solve Newton's second law equals zero equation. Sum of forces equals zero, sum of moments equals zero.